Hi, I'm Yarimjan. Today I will be presenting the paper Masking Methods, Unlocking the Spatial Listening Capabilities of LLMs for 3D Scene Language Understanding. 3D Scene Language Understanding includes a range of tasks for understanding and describing 3D scenes in natural language. There are three main subtasks: visual grounding, dense captioning, and question and answering. Recently, LLM-based approaches that tackle these tasks within a single unified framework have been actively studied. Existing works have focused on the input side of LLMs, so the decoders still use the standard cursor mask from language models. However, we found that directly applying the cursor mask to 3D scenes caused two problems. The first is sequential bias. Object tokens in a 3D scene have no inherent order, yet the cursor mask imposes an artificial one. As shown on the right, even for the same scene, changing the input order alters the context each token can attend to. The second is limited cross-modal interaction. Due to the cursor mask, earlier object tokens cannot attend to later instruction tokens, restricting their interaction. To address these problems, we propose 3D-SLIM, which consists of two components: geometry adaptive mask for resolving sequential bias, and instruction-aware mask for resolving the limited cross-modal interactions. First, the geometry adaptive mask. Just as humans naturally group nearby objects when perceiving 3D space, GeoMask dynamically adjusts each object's attention range based on its local density. It measures the average distance to all other objects in the scene to estimate local density. If that distance is short, the object is in a dense region. Then assigns more attentive neighbors for dense regions and fewer for sparse regions. This enables attention based on spatial relationships rather than input order. Next, the instruction-aware mask. The standard cursor mask prevents object tokens from attending to instruction tokens that come later in the sequence. Instant mask resolves this by allowing direct attention between object and instruction tokens regardless of their position. Here are the experimental results. 3D-SLIM can be applied by simply replacing the cursor mask with no architectural modifications. We applied it to both chassis and 3D graph LLM and observed significant performance improvements across all tasks. We also verified the effectiveness across different LLM backbones. Experiments on Vicuna, Llama 3, and QN all showed consistent improvements, confirming that 3D-SLIM is a decoder-agnostic approach not tied to any specific LLM. For the ablation study, we confirmed that GeoMask and InstMask work complementarily. For GeoMask attention range, the best performance was achieved with min equal 2 and max equal 10. We visualized the attention maps of the output tokens. For the question, what is next to the table beneath the TV, 3D-SLIM correctly focused on the answer trash can and its surrounding area, interpreting the spatial relationships well. In contrast, the baseline concentrates only the nouns, table and TV, missing the spatial context and predicting the wrong answer. To summarize, we identified the sequential bias and limited cross-modal interaction problems. that arise when applying LLM decoders to 3D scenes, and proposed 3D-SLIM to address them. We validate its effectiveness and generalizability across multiple baselines and tasks. That concludes my presentations. Thank you.